This video is going to discuss how to work with a parallel series circuit by applying Ohm's law, Kirchhoff's current law, and Kirchhoff's voltage law. So as we see here, we know that we have Ohm's law. We know that we have Ohm's law where the voltage is equal to the current times the resistance. And then we have Kirchhoff's voltage law, which says that the sum of the voltages around a loop is equal to 0. And we have Kirchhoff's current law, which says that the sum of the currents at any point is equal to 0. So if we look right here at this point, we can apply Kirchhoff's current law, and we know that we're given in the problem here, this is actually problem 29 out of the book, figure 7.92, and we are given that the current coming from the source, the electromotive force supply here, is 70 milliamps, and we're given that there's 42 milliamps going down through this load resistor. So we can therefore, looking at this point, we can determine how much current must be going through R1 by using Kirchhoff's current law. So we take 70 milliamps minus 42 milliamps, which is going to give us 28 milliamperes. All right. So remember, if we're putting this in Blackboard, we need to use 3 significant figures. So we know there we've got 28 milliamps. Now if we look at this point here between R1 and R2, let's just label these points. I'll call this point A, and we'll call this one point B, and this one down here then will be point C. And so here, point B, they're telling us that, we have the 28 milliamps coming down, and we have the 10 milliamps, which is going down through our load 2, resistor of load 2. So that means that we're going to be left with 18 milliamps, 18.0 milliamperes, flowing through the resistor R2. Okay, so I'm just applying, at this point, all I'm doing is I'm applying Kirchhoff's current law. We can pick any point in the circuit and determine what those currents are. So down here then at point C, we have 18 milliamps coming down, 8 milliamps are going to the right through resistor RL3, and so that leaves us with 10 milliamperes flowing through R3. So 10.0 milliamperes are flowing through R3. Similarly, if I was to look at the current right here at this point, that's the 42 milliamps going through load 1. If I was to look at the current right here, this is the 42 milliamperes plus another 10, so that's going to be 52 milliamperes. And if we look at the current right here, that's going to be added, and the other 8, which is going to be 60 milliamperes. And then at this point right here at ground, we have the 10 milliamperes going through R3 and the 60 milliamperes coming over here from the right, and so we're back to 70 milliamperes. So basically here, what they're not drawing in the circuit is that we have a DC supply here, E, and it's connected here down between ground and point A up here at the top. Okay, so using Kirchhoff's current law, given this problem, we're given these currents in different places, we're able to apply Kirchhoff's current law at the different nodes A, B, C. Call this one D if you want, and call this one E and this one F, and we can find the currents through every wire in this circuit using Kirchhoff's current law. Now we can apply Ohm's law and we can find out what is the voltage E. Well, if we look here, we know that this node up here, given this node up here and the ground node, E is connected to this top node and the ground node. And we know this resistor, so here's a resistor which is 1.2 kilo ohms, and we know we were given in the problem that there's 42 milliamperes flowing through it. So with that, we can find the voltage being dropped across RL1, which is actually also going to be our supply voltage E. So if we flip over to our calculator here, and I'm going to take my 42, so E, the supply voltage ends up being the 42 milliamperes, so that's 0.042 times the 1.2 K, so that's 1220. So that gives me 50.4 volts. So we have here 50.4 volts. Okay. All right, so given that, so we know we got 50.4 volts here, and we know that we got 28 milliamps flowing through R1, and we were given that there's 48 volts here. We can determine the resistance R1, which is going to be the voltage, the voltage V1 is the 50.4 minus the 48, which is 2.4 volts. So V1 is 2.4 volts. And then we can find out that the resistance R1 then is going to be the 2.4 volts being dropped across R1, the voltage across R1, which is the 50.4 volts, minus the 48 volts, and then divided by the 28 milliamperes of current. So we take our 2.4 divided by the 28. Now that's milliamperes, so that's going to give us a kilo ohm. Okay, so we got 2.4 divided by 28 milliamperes, and so that gives us 0.0857 kilo ohms, which is actually then going to be 85.7 ohms. Okay, so there's actually no kilo ohms with that. It's 85.7, and then we have our omega symbol. So the resistance R1 is 85.7 ohms using Ohm's law. Similarly, we know we got 48 volts across load 2, and we got 10 milliamperes. So that's going to give us that this is going to be 4.8 kilo ohms. Okay, so notice that our load 1 had 40 milliamps, 42 milliamps, and it was 1.2K. And it had a higher voltage across it also. This one has a much smaller voltage, or much smaller current, slightly smaller voltage, but a much smaller current. And so, you know, it's about 1/4 of the current, which means that the resistance is going to be about 4 times as much. So the resistance RL2, 4.8. That's Ohm's law. We take the 48 volts, which is across this whole area here, right? And divided by the 10 milliamperes, which gives us 4.8 kilo ohms. Likewise, we can find the load resistance R3. We're given that this is 24 volts, so there's 24 volts here. So 24 volts divided by 8 milliamperes. And so 24 divided by 8, that's going to be 3. So that would be 3.00 kilo ohms. And similarly, we can find R2. We could find here R2 has 48 volts minus 24 volts. So the voltage across V2 is 24 volts. And the current we already determined by KCL was 18 milliamperes. So we can find the resistance R2 is going to be the 24 volts divided by 18 milli. So dividing by a milli, we're going to get a K out of that. So we have 24 divided by 18 gives us 1.33 kilo ohm. 1.33 kilo ohms. Okay, so that's our resistance for R2. And likewise, we can find R3. R3 has 24 volts dropped across it. Here's our 24 volts being dropped across R3. And so the given Ohm's law, we can find, we know that the current's 10 milliamps. So it's 24 divided by 10, so it's going to be 2.4 kilo ohms. So R3 is 2.4 kilo ohms. All right. We can also calculate the total resistance seen by the supply source E, right? Using Ohm's law, we can say that the total resistance, our total, is equal to the 50.4 volts that we found E to be divided by the total current, which is 70 milliamperes. So if we flip over to our calculator, we got 50.4 divided by 0.07. This gives us 720 ohms. So the total resistance is 720 ohms. So it would be 720 for 3 significant digits. Remember, because of that 0, I must put a period here, and that's just going to be ohms. Or we could put it in Blackboard as 0.720 kilo ohms Either answer is correct. Okay, so we solved the problem. We used Kirchhoff's current law to find all the currents, and I have the currents in the circuit here all marked in a magenta kind of color. And so we found all the resistances, and then using Ohm's law for the total voltage, which was 50 volts, and then the total current. So the using Ohm's law with the total voltage of 50.4 volts and the total current of 70 milliamps, we found that the total resistance for the circuit was 720 ohms. So 720 period ohms. So now let's look at reducing our resistors. Okay, so we want to simplify this series parallel circuit, and so we're going to step it down one by one. So remember that if there's series resistors, we can combine them by simply adding them. And if they are parallel resistors, we use the 1 over R1 plus 1 over R2 plus 1 over R3 type equation to find those. So now we found R2, let me write that down. R2 was found to be 1.3333 kilo ohms. R3 was found to be 2.4 kilo ohms. RL3 was found to be 3 kilo ohms. Alright, now notice this one I wrote out to 5 digits because it's not an even number. The 2.4 is an even number, you know, it's all zeros after that. The 3.0 is all numbers after that. RL2 was found to be 4.8, and again it's after that it's all zeros. And R1 was found to be 28 that's the current through it. R8 was found to be 85.7. Now that was not an even number. So it was 85.714. 14 ohms. So since it's not an even number after that, I'm writing it out to 5 digits to make sure that I don't lose accuracy during my calculations. Alright, so what we want to do is we want to look at this circuit and we want to identify what's in series or what's in parallel. And so the first thing that I can see in this circuit is that R3 and RL3 are in parallel. So these two are in parallel with each other. And so we can use the equation. I'm going to call this resistor R33. So I'm going to take these two parallel resistors and replace them with a equivalent resistance using the parallel equation. So we get 1 over 2.4K plus 1 over 3K. Now, when you're doing the calculations, if all of them have K's in them, you can kind of leave the K out and just remember to add it back in when you get to your answer. Alright, so now when we do that, if you calculate that answer, you're going to find that to actually be 1.3333 kilo ohms. Now, looking at that, let's look at this. This resistor here had 24 volts across it, and it's got 18 milliamps flowing through it. So let's now look at that. Look at R2. Remember, R2 had 18 milliamps flowing through it, and it had 24 volts across it. So, you know, we can kind of look at that and say, well, wait a minute, you know, this had 18 milliamps, and we were told that there were 24 volts across it, and then we're told there were 48 volts here, which means there's 24 across R2. So guess what? R2 is 1.33333 kilo ohms, and this combined resistance of R3 and R load 3 is also 1.3333. And you know, that's just the way this circuit worked out. It doesn't always happen that way, but sometimes you're going to see those similarities pop up. And you know, it's a kind of a quick way to kind of double check your work when you're like, oh, wait a minute, that's 24 volts and this is 24 volts. They got the same current. They must be the same resistance values. So what I've done then is I've redrawn the circuit here with this equivalent resistance R33, which we found to be 1.333 K, and then I've already marked that R2 was 1.333 K, and now we can see that R2 is in series, right? All the current coming down through R2 is got to go through this combined resistance now. That's at 18 milliamps. There's nowhere else for it to go. So these two are in series. And so we can simply add those up, and that's going to give us then 2.666. And then, you know, technically this goes out forever, but you can round up to a 7 if you want there. But if you just make sure you carry out enough digits, you'll be safe there. So so over here, we'll call this resistor R233. Okay, so I just kind of like to try to keep track of that. So that's resistor R233, an extra 3 there. And so then we come down here. So here's my resistor R2333, which was 2.6, bunch of sixes there, kilo ohms. We had the R1, which was the 85.714, and RL2, R load 2 was, look back over at the other picture here, RL2 was 4.8K, and we can see now that these two, R233 and R load 2 resistors, are in parallel. So I'll call that R2233. I mean, you could put the L's in there if you wanted, but it's just a matter of trying to keep track. And so these are in parallel, so that gives us a 1 over 2.6666. Okay, and remember there's a K in there, but the RL2 also has the K, so we can kind of just leave that out for the calculations and put it back in at the end. And so when we solve that, R2233 now comes out, this is parallel. Remember, when it's in parallel, it's going to be smaller than the smallest of your resistors. So I'm looking for my answer to be less than the 2.66. Okay, and in fact, when I calculated that, I got that to be 1.7143 kilo ohms. Okay, so that is this equivalent resistance of these two combined. So again, I redraw. So remember, you always want to kind of find some resistors, combine them, and then redraw. So here is my R2233 resistor, and this one was 1.7143 kilo ohms. And then R1 here, let me write that back in here. This was 85.714. 85.714. and that was ohms. That's not kiloohms. This is simply ohms. Okay, but this one is kiloohms. So we're going to add 85, right, over here to our 14.3. So we're going to add 85 to that. And if you add it up, keeping at least 5 significant digits, it turns out these two, right, these two are in series. That's why I'm adding them up. So we've got R1 is in series now with this combined resistance we found before. And so we just simply add those up. So I'll call this one R12233. R12233, and it turns out that that comes out to be a pretty nice 1.80 kiloohm resistance. Alright, so we have 1.8 kiloohm resistance in series with a 1.2. Now, just to double check, think about this. This 1.8 resistance has 28 milliamperes running through it, and the 1.2 has 42 milliamperes running through it. So we would expect that this resistance, whatever it turned out to be, since it has a smaller resistance, or I mean a smaller current running through it, excuse me, it has a smaller current running through it, we would expect that this resistance to be more than the R load 1, which has 42 milliamperes running through it. Right, so there's only 28 milliamperes over here on the left side, so it's going to be a higher resistance because current always follows the path of least resistance, but they both have resistance, but you get more current in the smaller resistance. So 42 milliamperes is flowing through 1.2, and only 28 is flowing through the 1.8. Okay, so now we're going to look at those. All right, so that gives me this 12233 resistance here, which we calculated to be 1.8K. And so these two now are in parallel, which will give us one final resistance here, which is our R total. So our total now becomes this 1 over 1.8K plus the 1 over 1.2K. And if you calculate that, I sure hope you come up with 720 ohms. Okay, remember the period. You need the period there because of the 0 to make it 3 significant digits. Alright, but this resistance here, 720 ohms, is the total resistance of this circuit. So if you remember, that's, if we go back and look, alright, that's the resistance that we had calculated up here using Ohm's law by taking E divided by I total and calculating that. So if those don't add up, you know you've made a mistake somewhere. So one of the cool things about these circuits when you're working through them, if you take the time, you can go back through and double check things. Make sure that, like when you calculated here, we were calculating parallel resistors, for instance, and the answer should be smaller, if they're parallels, should be smaller than the smallest of that you started with. Okay, and so you can always double check your work with this, because we can apply the different laws and compare, and we should always get the same answer no matter which way you calculate it.